So where we left off. What was the last thing we did? We did that. No one can tell me what the last thing we did.
So if I remember correctly, the last thing we did was circular conductor. H at the center of a circular conductor. I'm not sure though, sir. I wasn't there.
Yes, sir. You did circular loop.
We did that.
Yes, sir. Both here. Ampere circuital law.
Yeah, if I remember correct, this is where we said we were going to start. Ampere circuit law. Am I correct?
Yes, sir.
Because I remember explaining that in electrostatics, the Gauss law is useful to obtain E. All right. So the parallel is Ampere circuit law in the in magnetostatics. Right? So similarly, in the magnetostatics, the complex problem can be solved using a law called Ampere circuit law, or Ampere's work law. Let me see who is here today with us. Seems that we have a lot of people logged in today. I hope they didn't just log in and leave. I have to have a record of who is attending class. Okay. So, Ampere circuit law. The line integral of a magnetic field H around a closed path is exactly equal to the direct current enclosed by the path. So H dot dl, the closed part is this. So this is the mathematical expression for this verbiage. The line integral of magnetic field intensity H around a closed path is exactly equal to the direct current enclosed by the path.
Just to clarify, sir, this is the current through that conductor, right, sir? When it mentions direct current, sir, it's talking about direct current to the conductor in question.
Exactly.
Okay.
So you have a conductor, right? And you have a current flowing through it. So you have a magnetic field around it, right? So what this fellow is saying is that if you know the magnetic field around it, and you do the line integral around the conductor, and you dot that with the magnetic field, it is equal to the current enclosed. So can you see the parallel with Gauss's law for electrostatic?
I understand this, sir, but I'm not sure. I don't really see the parallel, so where's that?
Well, tell me what Gauss law states.
That the charge of a body can be calculated using the charge on the surface. I know that's too vague. The surface integral, sir, of a normal component of a body is equal to the charge contained in that space.
Gauss law, in simple terms, Gauss law said the charge leaving the charge in the element is equal to the charge leaving the element. So if you have a surface and you have charge leaving that surface, the charge leaving the surface, the charge leaving the element is equal to the charge enclosed.
Yes, sir.
So for magnetostatic, this is the Ampere circuit law is a similar or parallel expression. So let us look at it in details now. Consider a long straight conductor carrying direct current I placed on the z-axis, as shown in the figure. We'll move down to the figure shortly. And we're going to consider a closed circuit path. Okay, let's move down to the figure. So here, you have a long straight conductor in the z direction. Right? Carrying a current I. So consider a closed circular path of radius r, which encloses a straight conductor carrying direct current I. So here is your circular path. Granted, if you don't like the circular path, you can choose any path you want to choose around the conductor. But everybody would choose a circular path because it makes whatever. We have to know the length because we are going to integrate along the circular path. So you don't want to choose one zigzag or go around or one whatever. You choose a nice circular path around because that integral is easy. So consider DL as at point P, which is a phi direction tangential to the circular path at point P. So here's point P. We're going around, right? So we're gonna consider DL at this point, a small element going around. So any point you choose, it will be tangential to the circular path. So DL is R d theta a d phi a phi. Do you understand that?
So when you say any point, you mean you don't necessarily have to start at point P, you can start anywhere on the circular path.
Turn on your radio. Talk
Oh,
again.
sorry. So I'm saying that when you said any point, it means that you don't.
I'm hearing so something in the background is over. Yeah. Go now.
You still hearing me, sir?
I'm hearing you.
Okay. So I'm saying that when you say any point, right, it means that like around the circular path, you don't necessarily have to start at point P. You can choose like any point on that path.
You're in a different class because I'm still hearing like somebody teach.
Yes, sir. See, and there's nothing else, sir. You can hear me now, right?
Yeah, I can hear you, but I don't want the other thing disturbing me. Go ahead.
I'm saying in relation to the circular path, right? You pinpoint point P. So I'm saying that you don't necessarily have to start at point P. You can choose like any path, anywhere in that circular path.
Anywhere.
Just a clarification, yeah.
Yes, anywhere, because R d theta. Okay, we establish the direction. R d phi. Because any segment, any small segment on this circular path would be R d phi, right? D phi means the angle. Because going around the circular path, the complete circumference would be 2 pi, right? So the distance around would be 2 pi r, right? d phi would be the fraction of 2 pi that you go around, right? So this r d phi would be around the total path, the length would be r times 2 pi. 2 pi r equal the distance around a circle. And a phi is your angle, is your direction.
Yeah.
Right? So d phi would be your small segment of 2 pi. Right? So h what we obtained before, H with the Boyd-Savart law, which is a long way, H around was I over 2 pi r a phi.
So, sir, in that case, if, for instance, it wasn't a square but a rectangle or a square, instead of 2 pi r, we would have to use the area for a rectangle.
Not area, the length. So we would have to integrate from along this. Say you had chosen a rectangle, which we don't even want to go there because suppose we choose a circle, a path like this, we would have to integrate along here, along here, along here, along here. Right? So we just want to choose a path, a closed path, which is less stressful to give us the distance.
AKA the circle.
Right.
Okay.
Sir, how would it be possible for you to change that path? Because instead of being circular, there are a method you would follow to get another shape of.
Yeah, that's what I just said. You can choose any path you choose, any enclosed path. But to figure out the distance around that enclosed path, you want to choose the easiest enclosed path. You could choose a rectangle, you could choose a ellipsoid. You can choose any path you desire. But we are choosing a simple circle to make it easier to find the distance around the closed path.
So you wouldn't have to modify the DL and the unit vector to get the other shape also. So.
That's exactly what I'm saying. Say you choose a rectangle like this, you'd have to integrate to the X along the AX, to the Y along the AY, to the minus X, and to the minus Y. So if you choose a rectangle, it would be four integral instead of 1. So if you have a straight conductor, your first order of business is to choose a closed path to make it the easiest for you to find that distance. Right? So that's why we choose the circular path, where your distance around the circle is RD phi A phi. Now, earlier we determined that H equal I over 2 pi R A phi. Right? And your HDL now would H dot DL would become this, that A phi dot A phi That is 1. So it comes to this. Just get rid of the A phi. Right? And your R cancel. So you get to this. So when you integrate this now around the entire loop, you go from 0 to 2 pi. So it becomes just multiplying this by 2 pi. And this cancels this. So we have just proven that H dot dl around the closed path give you I. Because we have already determined from Boyd-Savart that this is H. So we prove that H dot dl around the closed path give you I. Any question?
Oh, 1 second, sir.
Go ahead.
As in, no, as in, can go back up, sir, to calculation. I try to take it in, sir. All right, sir. I think I didn't get it, yes, sir.
No, all right. So we're gonna look first at H due to an infinite long straight conductor. So here's your infinite long conductor along the z-axis carrying a direct current I as shown. So again, we choose a circular path. We again pick a point. You can choose any point. It's gonna be the same, DLA phi. Radius R, and hence P is at a perpendicular distance R from the conductor. The magnitude of H depends on R, of course, and the direction is always tangential to the closed path A phi. So H has only component in A phi direction, H phi. All right. Consider the elementary length dl at point P in cylindrical coordinate. It is R d phi as before. So H is H phi in the A phi direction, and dl is R d phi A phi. So H dot dl is H phi A phi dot R d phi A phi is this. According to Ampere's circuit law, the integral around the closed path of h dot dl is I. So h phi r d phi around the closed path, which is 0 to 2 pi, is this. Which is this. So h is this. Now, if you notice, to prove here, we take h from the Boyd-Savart law, and we prove that h dot dl around the closed path gives us I.
And wait, sir, does this go for all closed paths or just for this case where it's a circular one?
I think you asked that question already. You know. I said you can choose any path you want to choose, any closed path. However,
No, what I mean, sir, is because I get that we do the derivation, the proofing using a circle, right, sir? But then I want to know if this formula now that we've now got is like, it's just proven to work for all closed shapes.
let's go back to the definition.
Let's check on the so,
This is your definition. The line integral of the magnetic field intensity H around a closed path is exactly equal to the direct current enclosed by the path. So
all right,
It's any path.
any closed path you want to choose,
you choose it.
you choose it. But if you choose one, if you choose, put it this way, right? If the line integral, if your conductor, right, run straight down the main drag U-tech, right? And I choose a closed path, when me just jump out of it, go under it, and come around. And you want a choose path where go a Ligani, go downtown, go a Tivoli, and go around. It no matter the closed path, you have to go around the closed path. So you will have to determine how you going to simply calculate that closed path. We are saying that if it's a line integral, if it's a wire, the simplest closed path to calculate that distance around it is to just make a circle around it. But any closed path you choose, it's quite all right. It's just you to find your distance. You get it?
Yes, sir.
So I was saying that here, what we did, we take the H that we calculated using our Boyd-Savart law, from first principle. And we prove that H dot dl around the closed. Yeah. We take the H from Boyd-Savart law, and we prove that H dot dl give me I. Now here we have H is equal to that, dl is equal to that as before. H dot dl is that. And we have the law, Ampere circuit law. We said the integral around the closed part of H dot dl is equal to I. So H, we don't know what H is yet. We just know that it's in the A phi direction. But H dot dl equal to I. Right? And we go integrate around the closed path. So we get this. So we get H phi is equal to this, is equal to this, which is the same that we got using the Boyd-Savart law. So in effect, what we did, what we have done here is just go in the reverse direction, the reverse engineering of what we did above. See if you get that.
I'm on the side now, sir. I just wasn't sure before, but yeah, I kind of understand.
About the rest of the class, anybody else have any problem?
But sir, how I'm looking at it, sir, is like based on the unit vector, then each magnetic field line would be distributed about the line conductor according to that equation, sir. So like if you wanted to get a square, then you would just use a unit vector for each field line and integrate it up to that shape, sir, from
Yeah. I think I'm understanding what you're asking to a point, which, you know, is pretty much correct. So if you use a square, say you use a square and you align the square along the different axes, the X, the Y, and the, well, since the conductor is going in the Z, you'd align the square along the X and the Y. The field lines is going in the A phi. So you'd have to dot that with the X, you'd have to dot that with the Y, the negative AY and the negative AX. So it would be very, very complicated. You would get the same answer, you know, but it'd take you a million years. Okay. So let's look at a sheet of chart. All right. This is a perfect example. So consider an infinite sheet of current in the Z plane. So this is your X, this is your Y, this is your Z. So when you say the Z plane, that means it is perpendicular to the Z. The surface current density, K, is flowing in the positive Y direction. Hence, K is KY, AY, right? So here it is. This is how your current is flowing. So we are going to consider now a closed path around the current. So here, so we are going around the current now. This is how your current is flowing. So we are going around the current. But here we're not going to use a closed path because we want to make the integral around the closed path simple. It's a plane, you know, it's a sheet. So here we use a rectangle, right? And expand this in your mind, or shrink this in your mind, that this closed path is around the current. So in your mind, either expand this closed path or shrink this surface so that it go through the loop, right? So here's your closed path. From 1 to 2, that means here you go around. From 2 to 3, you go under. From 3 to 4, you go over this side. And from 4 back to 1, you're above here. You with me?
Fair enough, sir.
Yes, sir.
Okay. So the width of the path is B, and the height is A. So it's perpendicular to the direction of the XZ plane. The current flowing across the distance B is given by KY times B. So the current KY is the current per distance here. So KY times the distance is going to give you the total current crossing here. Consider the magnetic lines of force due to the current in the AY direction, according to the right-hand thumb rule. There's the right-hand thumb rule. So here is your closed path again. This magnetic field component cancel this one. All right? So we are simplifying what we have to calculate now. All right? All right. Hear how they say it now. In figure 733b, it is clear that between the two very closely separated conductors, the component of H in the Z direction are oppositely directed. Right? Minus HD for position 1 and plus HD for position 2 between the two positions. So all such components cancel each other, and hence H can only have component in the Z direction. So before you even start calculating anything, you almost solve the problem. So as current is flowing in the Y direction, H can only have component in Y direction. So H has only component in X direction. H equal HX, AX, for X greater than 0, and minus AX, AX for Z greater than 0. So here is your Ampere circuit law again. So you are going to only evaluate for part 1 to 2 and 3 to 4, which is DL is DZ AZ and DZ AZ.
So could you see the diagram once more on the equation?
That diagram?
So, yes, all right. All right.
Tell me if you follow that. Do you have any problem?
Say like someone who have just go over. It's like it's a lot to pack in on, so it's more like my try really to understand it.
So take your time.
So the on the integral sign is that 1 and 4 after the H that deal. Is it?
Which one?
Yeah.
Here?
Yes, sir.
Yeah, 1 to 4. Or 4 to 1.
So is it so you use a smaller upper limit and a larger lower limit?
No, you're not gonna look at it as the limit. Is look at it from the diagram.
What is the location?
It's 4 to 1 and 1 to 4 is not upper and lower limit, is actually the position.
So I have a question as well, sir. Before go back, sir. Where HZ they cancel out each other, sir. But I just want to clarify that HX also cancels out itself. The two HXs. You know, when you go over Y, they don't take account to counteract each other.
If you notice it's on the it's at Z equals 0 now.
Yes, sir.
Right? So no, if you look at the now the so Z would always be positive Z, right? But when you look at the X now, the X go from positive X to negative X.
Oh,
So
okay.
that's why that no cancel. Where were we again? Okay. So here, that's what you amount, which is what you got when you use the Boyd-Savart law. Okay, so when we come back, I'm going to leave you to do the Lorentz full.
Read that, sir?
Hold on. When we come back, we do the volume, and then we do when we come back, we do a little more, and then we do some example.
All right, sir.
All right. We're gonna do a little bit more, and then we do some example. But before you guys go, the on my university, I kill me, man.
What is wrong, sir?
So may I give no face-to-face final. But on not treat it thing good, man.
As in them say you can't do it or something, sir?
Eh?
Them say you can't do it or something, sir?
If we can do what?
What is the university saying in regards to that, sir?
Then say they not love the fact that me I give no face-to-face final. But them say so me I get because I'm not getting the work.
Feedback where you want.
So we don't know. If we don't have any ideas, we can still change it, but I'm not giving no like I'm giving the midterm or no copy.
I mean, sir, there's always, because I was looking over the syllabus recently, sir, and there was a thing about a little assignments there. Why I was wondering why I did scrap that.
Yeah, but I'm not giving an assignment.
No, sir, you haven't given us assignment.
No.
No, sir.
I'm not giving an assignment.
I think you said something about assignment with MATLAB, but you haven't.
Yeah, then that.
No, you only say assignment with MATLAB. That's all.
Yeah, in the curious, sir.
I'm not giving no the problem my son of use MATLAB and do it.
No, sir. You
No,
don't
sir. No, sir.
one N right there.
All right, I'm gonna give it. Yeah, all right, I'm gonna give it some.
Sir, you know, there was a weekend where you said you were going to send us a tutorial.
Yeah, but you did, yeah, and there was also the one where you said you were going to send us the questions and the solutions, but
Then if Mr. May I go do it, I'm not do it. What am I gonna not ask me for it?
sir, I kind of messaged you to ask you, sir, but you kind of seen the message, so I'm not sure.
Then I have my phone number, man. Yeah, I know something I got you all kind of stress and strain.
Understand, man, sir.
Two brother dead, one friend dead, and burned down my house and all that rest.
Oh, boy.
But anyway,
We'll remind you again, sir. All right.
all right. So see you now at 2, yeah?
All right, sir.
All right,
Cool.
sir.